The next example I want to talk about is skewed binary search trees. So I'm going to go back to the paper in a moment, but let me just go over Gert's slides because they explain the problem a bit nicer. It's nicer looking at the paragraphs of the paper. So we all know about binary search tree. So what's skewed binary search tree? So well, this is a perfectly balanced binary search tree. Every node has essentially, every leaf has the same depth. Okay, and you can make a binary search tree skewed by not putting the middle guy at the root. So if I go back to this picture, I have 16 elements and I have, or 15 elements, and I put the middle value at the root and then the left half to the smaller half to the left and the larger half to the right. Okay, but if I put some other number, let's say if I put 12 at the root, then there will be more elements to the left and fewer elements to the right. And that's how you can make a skewed binary search tree, by not cutting the elements in half, by cutting them at a different fraction. Let's say alpha fraction to the left, 1 minus alpha fraction to the right. So in other words, a perfectly balanced binary search tree has a skewedness parameter 1/2, which gives us essentially a balanced tree. But if I change this parameter alpha, then the skewedness of this tree will change. So for example, alpha equals 0.4, you can get a tree that looks like this. Alpha point 0.2, that you get an extremely unbalanced tree, and alpha point, let's say, what is it, 0.0105, you get essentially completely skewed binary search trees, just like a list. Okay, so with this parameter alpha, we can control how skewed a binary search tree is. You might wonder what's the point of it, because obviously a balanced binary search tree is the best, right? But don't go too fast. Interestingly, even in 1972, there was work done on skewed binary search trees. I have no idea why, but basically it is known how to calculate the average depth of a node. And as a corollary, we can also get how many comparisons that we need to do to find an element in a skewed binary search tree if I just search for a random element. And the formula is relatively complicated, but you could just summarize this chunk of the formula as h of alpha, because it doesn't really depend on any other parameter, it just depends on alpha. So let's say this is a function h of alpha times this value, and this is fixed for a fixed value of n, and this is also fixed for a fixed parameter n. And if you plot this, you get a picture that looks like this. So this is essentially how many comparisons you need for, I guess, for a particular, what is the constant behind the number of comparisons that you need. The lowest number of comparison is, you can see, is over here, which this is minimized, and that is alpha point 0.5. And as alpha gets more skewed, either to the left or to the right, the number of comparisons increases. Therefore, theory predicts that if you implement this, and if you run experiments on skewed binary search trees, if you search for random elements, then your behavior should look exactly like this. So what do we see? Well, in practice, that we actually see that. We see that the number of comparisons exactly follows what the theory predicts. So the number of comparisons are minimized for alpha point 0.5, and alpha goes to the left or to the right, it goes up. But what about the runtime? Well, turns out for the running time, we get something funny, that it seems like the best running time is achieved for when alpha is at this extreme. And then we cannot explain this by theory, because our theory cannot predict this result. Our theory says 0.5 should be the best. So what's going on here? And this paper is essentially trying to explain this phenomena and trying to bridge the gap that exists between theory and practice when it comes to just binary searches. Okay. Okay, let me just go back to the paper now. Again, the beginning explains the typical factors of modern architecture that affects the running time. That includes caches and so on. But this paper, following some previous work, highlights another aspect of modern computers that can impact the running time, and that is branch predictions. So a typical machine, let's say Intel machine or AMD machine, has a very powerful CPU. And what this CPU tries to do is that it tries to have a pipeline that is as full as possible. In other words, tries to execute, like, say, 20 instructions all at the same time by predicting what's going to be the next instruction that is going to be executed. But if you make a wrong prediction, for example, if you have an if statement that is a branch, then your machine, your CPU cannot predict exactly what is the instruction that is supposed to come next. So the CPU tries to predict what comes next. And if it makes a wrong prediction, then the pipeline essentially collapses. And that induces a cost, which means the CPU needs to work a bit harder. If there are no branches, then a program will actually run super fast compared when there are branches. And this is, they claim, is the explanation for the behavior that we've seen in practice. Now let's see if we can follow through this and we can show convincing evidence that the hypothesis that branch predictions are the one that causes skewed binary search trees to be faster than balanced binary search trees.